Okay, let's start. Do you have any questions? Okay. So let's continue, right? So far, right, the theme is still about exploring continuous random variables. And so, right, the features are the following. If you have a random variable x, then if it's a continuous random variables, then a PDF will be given. All right. That basically is non-negative, and the integral or the area under the curve, right, is 1, which, right, represents, by the way, is just the probability that, basically probability that x takes on some value, right? I mean, in case like there's something weird going on, you might have random variable taking on value infinity, but that's kind of a little bit beyond our class. Then there's a CDF, right, which is denoted by this capital F, which is between 0 and 1, and it represents, right, the probability that the random variable takes on, right, value less than or equal to x. And if you differentiate, right, the CDF, you get a PDF. So the CDF, right, is used one of the main use is to find the PDF, right, of a function of the random variable x. Okay. Again, the reason is because the PDF itself is not something. It's not a probability. So when you try to write down probabilistic statements, you can't operate with the PDF directly. You have to operate with probabilities, and probability by definition is working at the CDF level. But so what we're concerned with, right, is something along the line of a function of random variable x. But right, so basically finding the PDF of a random variable, right, a function of a random variable, is sort of like, it's not that hard, but let's say that it's something that will be reserved for, I think, 5.9 for further discussion. Okay? We talked about it a little bit just to demonstrate the use of the CDF. But for now, sorry, 5.7. Let's talk about the other the other result that's concerning the a function of random variable x, which is expectation, right, of a function of random variable x is the integral, right, of that function times the density. And again, right, I emphasize that this is a much easier result than finding the PDF, right? Because basically the claim is that somehow this is equal to x times the PDF of phi of x, right? The PDF of a function of the random variable. Okay. And so you understand that this is the definition of expectation. and y is equal to this is a theorem or a result, right? And we call it the law of the unconscious statistician, just kind of reflecting, you know, the statement that somehow, if you don't think too much about it, you might think this is obvious, but it's not, right? There's some result there. But what we want to focus on is, right, this whole point right here, writing, right, something, translating, right, expressing, right, an object or something, an object, right, as a function of the random variable. Okay. And you see that that's kind of like, so I mean, by the way, right, this is kind of under the bigger idea of modeling, right? When you model, you basically have to say what you're modeling, how you write down the mathematical expression, right, of whatever you're modeling. And that's really it, right? You expressing an object mathematically. And here you write as a function of a random variable. And so to demonstrate, right, I think we had the example last time where we say a stick, right, of length 1 is split, right, at a point U and uniformly, right, or randomly. I think that's basically, I guess, along the length, right? So this is the word that basically, without further qualification, means uniformly, right, along the length. Meaning, right, that this is saying U is a uniform random variable from 0 to 1, right, because the length is 1. And so find the expected length of the piece that contains the point P. All right, so we looked at this problem last time, right? And the point is this, that basically, so some of these questions you have to, or if you draw a picture, it will be more helpful, right? So you have a piece of length 1, and you have a point, right? That's predetermined, and you break it off somewhere, right? Let's say here, right? Uniformly, okay? So then, of course, the piece that contains P is this piece, right? If you break it off here, then the piece that contains P is this piece. On average, how long is that piece? Okay. And it looks confusing because the piece itself changes, right? Sometimes it's a right piece, sometimes it's a left piece, blah, blah, blah. It looks confusing. But I mean, that's what you use math for. You use math to kind of symbolically, at least right, control the ideas. So you kind of let X be, right, the length of the piece. That contains P, right? And you have, right, the point, the coordinate of U, right? This is the coordinate system, right, from 0 to 1. You have the coordinate of U to begin with, right? Even though it's a random coordinate. And the whole point is you try to express X as a function of U. Okay. Well, why? Because then you can use the law of the unconscious statistician, right? Notice they're not asking you for the distribution of the length, right? They're not asking you for well, you know, what's the PDF of this length, right? Of the piece that contains P. No, they're asking for the expected value. And again, right, expectation is, let's say, a much easier thing to do. You just have to find this function and multiply with the density. By the way, right, do we know the density of U? Yes, we do, right? It's just going to be 1, right? Like that. So, okay. So, well, what would that be, right? So, again, right, it, like I said, it might seem a little bit difficult. We just have to think about, well, where can U be, right? U can be anywhere along the length, right? The piece of, but if U is over here, and by over here we mean what? Less than P, right? If U is less than P, you can include equal, right? Doesn't matter how you include it. Then, right, clearly the piece that contains P, the length of it is 1 minus U, right? And U can be over here, which means that, which is the case that U is bigger than P, right? You can include this if you want, but you know, by default, right, U is less than 1. So yeah, but, and then what's the length of the piece? The length of the piece is U itself. And there you have it, right? That's the function. And I guess, right, this whole nature of, you know, when we just superficially look at, we see the right piece and the left piece, blah, 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 sort of is the piecewise nature of the function, right? The function x. But, you know, so you can, if you want to even more, be more pedantic, it's a function of U equals 2, right? But the whole point, right, is that the law of the unconscious statistician doesn't require phi to be any type of function. We normally see x squared, x cubed, blah, 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 when we deal with moments, but any function, right, would work. And so, including piecewise function. So therefore, right, the answer is very simple, expectation of x, which is the integral from 0 to 1, but rather, right, so you can do this if you want. F phi of, I guess I rather do, you know what? Here's the thing, right? If I want to stick with my notation, this will be capital U and this is little u. But capital U and little u is hard to distinguish on my tablet. So, but like that, right? This is capital U. So phi of now little u, the density of the capital U, function of little u du, like that, okay? I mean, if you want to kind of write down everything, but then it will be integral from 0 to P of 1 minus little u du plus the integral from P to 1 of U du, whatever that is. I'm not super interested in the, you know, calculus at this point, but it's more like about the process, right, of expressing something as a function of a random variable. Are we clear on this? Any question? All right, so let's take a look at a few more. I think the first one is, let's say your question 510, right? This is not about really, it's just about reading comprehension rather. A train, right? Trains rather than a train. Headed for A, arrive at the train station. uniformly. Sorry. Uh, at a 15-minute interval. Starting at 8 p.m. 8 a.m. Starting at 7 a.m. actually. And then trains headed for B. Arrive at the station. At 15 minutes interval. Starting at 7:05. Okay. And then a passenger arrives uniformly, right? At the station uniformly between 7 a.m. to 8 a.m. And gets on the train, gets on the first train that arrives. What proportion of time do they go to destination A? So this is also a question about modeling, right? And we talked about the uniform distribution last time as well. And I kind of said that one way to visualize the uniform distribution is like kind of a time, right? Arrival time. But you do know, like within some time window, so like 7 to 8, right? So this is sort of that question, but it requires you to kind of imagine and interact, right? This with something else. So how do we do this question? So that's 7 to 8, right? When do you travel to A? Well, you travel to A, right? If your arrival time is after B and before A arrives, right? So for example, so it's sort of by default, right? You will miss the train arriving at 7, right? Going to A, because the probability you're arriving on the dot at 7 will be 0. So if you arrive anytime in this time interval, you will go to B. But if you arrive anytime between this time window, you will go to A. Agree? And it's just that theme, right? So for example, the next one will be 7:20, right? To 7:30. So B, A. Again, between this, you go to A. Do we understand? So with that said, right, what's the probability that you go to A? Go to A. What else? Right. And any of these 4 time intervals, you will go to A. And each of them, right, has length 10. So the probability is 4/6. Any question? Okay, so 5.11, a point is chosen at random on a line segment of length L. Interpret this statement and find the probability that the ratio of the shorter to the longer segment is less than 1/4. So first of all, right, interpret the statement. We know what this means, right? Because I mean, why do they want you to interpret the statement? Because the word is chosen at random could be vague, right? They're not giving you the exact distribution. But I mean, it's sort of like implied by convention, right? When you say you choose something at random, what do we mean? We mean that we choose it uniformly, right? No preference. So basically the point, when you break off the segment is uniformly from 0 to L. Okay, like that. And then, right, they want to find the probability that the ratio of the shorter or longer segment is less than 1/4. So how do we do this? So again, you see, right, this is the theme of a function, right, of a random variable. The random variable here being u, right? And what are we looking at? We're looking at x, which is the ratio, right, of the short to the long segment, right? And what's our task? Our task is to express x as a function of u. What is x then? Well, if u is less than L/2, then the shorter is u and the longer is L minus u, right? So u over L minus u if u is before over 2. And by the way, you can throw inequality or not. Here, you can afford to be careless, again, because U is a continuous random variable, okay? But if it's discrete, meaning that, or it's a mixed, meaning that somehow there's a chance that you can take on some value like over 2 with some positive probability, then you have to be careful where you put equality. Now, on the other hand, right, if you use over here, then clearly, right, the shorter part is this and the longer part is that. So it's L minus U over U, over 2 less than U less than L. Okay. So that's the random variable. What are we asking? We're asking what's the probability that is less than a quarter. So there you go. Probability X less than a quarter. But after you express like this, you can clearly see what's going on, because that will be probability of U over L minus U is less than a quarter, and U is between L over 0 to L over 2. Or, which is adding here, probability L minus U over U is less than a quarter, or L over 2 less than U less than L. Right? And we can add them because here these two events are mutually exclusive. So any question? Now the rest of it is just manipulation, right, of the expression. So I'll leave it to you, right? But the key here again is about the writing, right, of the random variable as a function. The random variable we're interested in as a function of another random variable. Okay. All right, so let's look at the next one. So a bus travels between A and B, 100 miles apart. The bus breaks down, right? I mean, if it does, uniformly, right, at a location uniformly between A and B. So there are two options. Option one, so you have to service the bus, right? Option one is to place the stations at, A, B. So there are three service stations, right? This one is at the 50th mile, right? So in between. Option two is to place, I think at the 25th miles, 50, 75. They ask which option is more efficient and why. So first of all, right, what are they asking? And how do we approach a question mathematically?
We want to minimize the distance to a service station, or the average distance you'll have to go.
Yeah, well, there's no minimization here per se, but you between the two options, you compare which one's smaller. Correct, right? Yep. So you let x be the distance, right, to the nearest, right, service station. I mean, in both options, so you can call one of them x1 and one of them x2. It doesn't matter, right? And you calculate expectation of x, and you want to choose the one with a small expectation of x. Okay, and that's the meaning of efficiency here. So for example, what is expectation of x in the first case? Which means what? Actually, before this, what do we need to do? We need to write x as a function of u, where what is u? U is the location, right, of the breakdown. So u is uniform from 0 to 100, right? So what is this function? Because, right, you're gonna try to find its expectation. So what is this function in both cases? So it will be, right? Well, if you break down before the 25 mile mark, then A, right, is the closest one, or it's really U, right, if U is between 0 to 25. If you go beyond that, between 25 to 50, then the mid, right, station is the closest. Actually, right, between, so 50 to 75, the mid is still the closest. But of course, now it's U minus 50. And finally, right, between 75 to 100, then the station at B is closest, right? So again, you see the theme of what? Piecewise defined function, right? You've seen actually piecewise defined function in all these examples. Why? Because they're cases. That's all there is, right? Piecewise function denotes cases. Whenever you have cases, piecewise functions in the air, right? And then you just have to multiply this with what? 1 over 100, right? du, and find the expected value. Okay, so far? With option 2, what do we have? With option 2, right, from 0 to 25, it's going to be 25 minus u, right? Because there's no station here, by the way, right? The first one is here. So it's going to be 25 minus u between 0 to 25, right? But then here, you start to have midpoints, right? Depends on which one's closer. So something like u minus 25 if you are between 25 to 37.5, right? And then 50 minus u if you from the 37.5, 50, and then u minus 50, right? If you're in the midpoint here, 62.5. And then you also have the midpoint here, right? 75 minus U. But if you go above, right, beyond 75, then 75 is the closest. All right, like that. And then again, right, this is a piecewise function. And then you take this and you multiply with 100 EU, and you compare the expectation of the two to see which one is more efficient. Any questions? All right. Next question. So this is question 5.13, but well, let's just do question B. So a bus, right, arrives uniformly between 10 to 10:30 a.m. and you arrive at 10 a.m. So question B asks, if at 10:15 the bus has not yet arrived, what is the probability that you will have to wait an extra 10 minutes? How do you solve this question?
The remaining probability is uniformly distributed in the remaining time between 10:15 and 10:30, right?
Yeah, you can do it that way, which is called the conditional distribution, right? Which is slightly more advanced, which is correct. I think what you said is not wrong, but I prefer to do it a little bit more elementary, right? In a more elementary way. How so? So what you said is right, but I think it needs some concept that we haven't covered yet, which is conditional distribution. Let's say this, right? We can do it more simply than this, more simpler, right? Like this. U is a uniform from 0 to 30, right? Basically. This question is what? It's a conditional probability question. That's all you have to recognize. What kind of conditional probability? Conditional probability that U is less than or equal to U being the arrival of the bus, right? So it will have to arrive after 25 for you to wait an extra 10 minutes. If it has not arrived at 15. Agree? That's it. That's the interpretation of the statement. Not arrive at 15, conditioning, wait an extra 10 minutes. The reason, right, is because this is by definition like that, which doesn't require any advanced concept, right? It's just about interpreting, right, the statement. Any question? All right. Last but not least, (5.31). A, right? Basically, they say a random variable X is uniform 0 to big A. Well, there's a story attached to it, right? You can call it, whatever. Breakdown, right? Location of the bus, blah, blah, blah. And you want to place a service station or a fire station, whatnot, right? Somewhere between this road. The question is where, right? So find A so that A minimizes. So that we minimize this. And this is literally, right, a minimization question. Because here we choose A over something, right? It's not just two options. I mean, I hope it's clear, right, that A here is in between 0 to A, right? Did I say that? Nope, did not say that. So A can be anything, right? So in theory, right, A is in a real number, right? How do we do this? So the question really is a calculus question, right? So first of all, right, I mean, I hope it's clear that even though potentially A can be any real number, you should put A between, right, within the road to minimize, right, the distance. No one will be crazy enough to, right, put the one outside, right? So that much is clear. And then within that, right, what is expectation of X minus A? Well, just apply the definition. It'll be, right, the absolute value of X minus A. But if X is less than A, then it's A minus X, right? And then 1 over capital A for the density dx. But if X is above A, then you got that as the absolute value. Okay. Any question? And then, of course, right, this can be calculated. So I think this is A minus X squared over 2. Let's see if that's true. Sorry, it's not A minus X squared. It's A squared over 2, right? There's 1 over A here, won't do anything. And then this one is A minus A squared over 2. Agree? And so we're minimizing, right? So what do we do? We differentiate with respect to A, right? Little a, okay? And set it equal to 0, which is, well, 2a goes down to a, right? So we can keep the big A, but it won't do anything. And then the second one would be minus, right? A minus A. That must be equal to 0, which, as you can see, is what? 2 little a equals big A, or A is A over 2, right? As the answer. So what we're saying, right, that of course well, not of course, let me be careful, that the location that minimizes the absolute average distance between, right, uh, you know, to between the random variable, right, and that point is the midpoint, right, between the two ends, the extremes. The only thing I want to say here is that, right, first of all, this is how you solve the problem. You can't really conclude that this is an obvious result for any reason, because this is like the simplest thing that you can do, like in terms of the problem. But the two most common variation is the following. You could minimize the absolute value, which is called the L1 error, or a more, let's say, yeah, not a more popular one, but let's say an equally popular choice is the L2 norm, or mean square error. People like to do this because it tends to give nicer result, right? Like linear regression. So that's the first thing. And you can bet that these two doesn't necessarily give you the same result in terms of the choice. Here, unfortunately, it still gives you the same choice if you use the uniform distribution. The reason is because the uniform is very, very special. But the second variation is that X has some other distribution rather than a uniform. And this is a more interesting choice, right? And which is part B of this question, right? That we'll take a look soon after we cover the exponential distribution. But the point being is that, right, this answer doesn't have to be an obvious answer in it for any reason. It just happens to be this way, which is kind of intuitively okay. The reason is because, the the location, right, of, let's say, the accident or the breakdown, whatever, is uniform between 0 and A, right? All right, any question? Okay, so let's continue with our discussion. So far, right, we started to discuss the family, right, of well-known random variables. And the first one we started with is a uniform, right? Alpha to beta. You know what? Let's call it uniform A to B, right? So the uniform has several properties, right? The first thing is that the density, of course, is a constant. between A and B. And 0 otherwise, right? Its expectation is a midpoint. Its variance is B minus A squared 12, right? Again, we've done these calculations before, so I won't repeat, but, and again, right, the point is that this is better, these are better committed to memory than to recalculate every time, but you should know it anyway. And then if you look at the basic level of transformation, meaning you do, let's say, Cx plus D, right? Meaning you change the location and you stretch the random variable a little bit. Then basically it's still a uniform random variable with the ends move accordingly. Let's say C is positive, right? So that we don't switch the order between these two ends. And again, this might seem like super obvious, but I want to caution you that not really, if only from the pedantic point of view, that some random variables, as we'll encounter, like the exponential, will no longer be called exponential if the support, right, is in some region, like a negative value. The uniform is a uniform, doesn't matter if A, B are negative, positive, whatever, it's always uniform. But some other distribution has, the name is traditionally attached to certain special region over the real line. So this fact, I mean, it's not that remarkable in any sense, but it's still worth paying attention to in contrast to some cases where no longer the case, okay? But also, I guess the point is that when you do a linear transformation of a random variable like this, and this is like the mildest thing you can do to a random variable, stretch it, or what do you call it, like condense it or whatever the term is, and then move it by a location. You really don't change the shape of the density in any essential way. You have to do something more dramatic, like take a square, do an exponential, do some other functions, or like take the piecewise function of x to change the density in any more dramatic way. All right. Let's see here. I think we do have time to talk about this problem as just as a cautionary thing. So this example is called the Bertrand's paradox, probably referring to the philosopher, mathematician Bertrand Russell, I believe. But anyway, so it says this. Consider a random chord of a circle. Find the probability that the length of the chord is greater than the side of the equilateral triangle inscribed in a circle. Okay, so that's a question. So what does this mean? So you have a circle, right? Doesn't look like a circle. Okay. And a random chord means what? Well, that's a random chord, right? Now, of course, an equilateral triangle in a circle has a fixed length, right? With respect to the radius of the circle, let's say. And there are many things to consider for the problem. One thing is, does the radius of the circle matter? In other words, right, does a radius change this probability in any way? And you can convince yourself pretty quickly that no, right, this problem is sort of like scale independent, meaning, right, things just scale up according to the radius of the circle. So without loss of generality, you can suppose that the radius is 1. But you can call it radius r if you want, right? But the point is that basically consider a random chord. What's the probability of the length here, right? Of course, if I draw something like this, it'll be greater, right? If I draw something like that, like I just drew, then it's less. Okay? What is the probability?
Is it 1/3?
Yeah, 1/3 is probably the most obvious answer. And the reason, right, is because if your one point, right, is kind of pick, and then the other point, you can think of it as randomly selected among the remaining of the circle. But then if you look at the angle, right, I don't know what is called a centered angle or something, right, the angle formed with the center of the circle of the chord, right, then you see that from this point, if the angle is bigger than, I don't know, what is it, 120 degrees, right, pi over 3, then the chord length will be bigger than the area of than the length of the equilateral triangle. And if the chord length is, if the angle is less than 120, then it will be less than, right? So the answer for that is with the view to the angle, right, formed with the center of the circle, and it's 120 over 360, or if you prefer to use radian, pi over 3, right? Sorry, it's rather 2 pi over 3, right, over 2 pi, whatever, right? It's 1/3, right? Nevertheless, there is another answer, which goes as follow. If you consider, right, so basically, obviously, right, you can always rotate the triangle, right, to be parallel to the chord, right? And so if you look at from the origin, draw a perpendicular line, right, to the chord, then it's just a fact of life. You can check that the equilateral triangle is exactly halfway along this radius. Is that okay? And clearly then, right, if you are in the, let's say the other half, this half, then you're going to be less than the chord. But if you're in this first half, then you'll be longer than the chord. Is that okay? So there's another answer, which is a half. Okay? And therein lies the paradox, if you will, right? There are two answers to the question. But you see where the answer to the paradox is, or I don't know why they even call this a paradox. It's really not a paradox. It's really just about, let's say, a vagueness of language. Because it's really this word right here, right, is the culprit. We've been using it casually so far, and we say random means uniform, right? And we still stay true to the spirit, but now it comes to haunt us, because in the topic of uniform, you can ask what kind of uniform if there are more than one target to be uniformly distributed. For example, this one right here is uniformly distributed over the angle, right, around the center, which is really, if you prefer, a two-dimensional object, right, which is because it's also uniformly around the circle, right, around the perimeter of the circle. So it's a two-dimensional uniform. I mean, it's really one-dimensional, right? But it's uniform around the circle, right? On the other hand, the 1/2 is uniform around the radius. And you can check that if you pick a point uniformly along a circle, you're not gonna find a point uniformly along the radius. Or if you pick a point uniformly along the radius, you will not correspondingly pick a point uniformly along a circle. So these are two different kinds of uniform, which are equally valid when you just say a random chord. Do you understand? So these are two different kinds of uniform. Therefore, these are two different methods of picking. Therefore, they result in two different answers. That's all. So, I mean, again, it has the big name attached to it, whatever. I don't know if there's anything deeper than that. But the moral of the story here, as far as I'm concerned, is that you have to be careful with your choice of word when there's more than one interpretation around. So even with uniform, right, if you have more than one target to pick uniformly over, you have to be careful because these may not be the same choice, right? Sometimes it is, like maybe choosing uniformly around a circle maybe is the same as uniformly around the radius, but you can check, and it's worth checking that they're not the same thing. If you pick uniformly along the radius, you will not be uniformly along a circle, and vice versa. Any question? All right, so that's it for the uniform, right? The second one, so that's 5.3. 5.4 is the normal random variable, which is, you know, a famous thing. Let me just maybe skip for now. Definitely we will not skip the normal in any way. It's just in the order of thing. I prefer to leave the normal to the last, maybe. And I'll prefer to, because it involves, you know, the central limit theorem, blah, 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 which we won't discuss until another chapter, but somehow it's kind of alluded to here anyway. So I want to reserve it until the end. And I want to move to 5.5 for now, which is the exponential lambda. All right. And so, of course, when you define a random variable, you have to start out with the density, right? So the density will be lambda e to minus lambda x, if x is non-negative, 0 otherwise. Okay. So lambda here is positive, right? Lambda is the parameter, right, of the exponential distribution. Just like alpha, beta, A, and B, where was it? Are the parameters, right, of the uniform. So again, this is connected to like statistics, for example, right? Parametric statistic, where you will learn how to estimate the parameters, right, based on the observed value of the sample random variable. But here we take lambda as given, and we just kind of try to find the behavior of the random variable. So the first thing you should verify for yourself, right, that this guy is truly a random variable, truly a density, in the sense that, right, the integral from 0 to infinity of this is 1, well, it's obvious by a u sub, And it's also non-negative, right? Because it's an exponential, right? What else? Well, the CDF for this guy is particularly easy because, well, what is it, right? The integral from 0 to little x, right, of lambda e to minus lambda, let's say u du, which is e to minus lambda u, so 1 minus e to minus lambda u, lambda x, right? But this is only true for x positive, right? X non-negative. And of course, it's equal to 0, right? If x is negative. Okay. And here, probably this is, I mean, the uniform you can also do it, but I didn't do the CDF of the uniform with you. But check this out, right? The CDF should satisfy what kind of properties, right? It tends to 0 on the left. It tends to 1 on the right. As x goes to infinity, this goes to 1. And, right, is increasing, right? Well, it's a little bit, you know, you have to check several things, right? This is e to minus lambda x is decreasing. So if you subtract a decreasing function, you're going to be increasing, right? So the CDF will be something like that, right? It's asymptotically approaching 1 as x approaching infinity. That's a CDF, right? Well, we have done some kind of calculation to show, sorry, there's an x here, right? So this is just integration by parts. And I'll skip that because we've done it, you know, once or twice, whatever, right? Integration by parts. It's not something fun to watch, but it's 1 over lambda. And the variance, well, again, right, is expectation of the square minus the square of the expectation is 1 over lambda squared, okay? Again, what's a proof? Integration by parts. Do I want to do it? No, I don't want to. I mean, I can, but it's boring, okay? So these are the 2 results. So now let's talk about some obvious use of the exponential. Obvious uses like this, okay? It's once in a while, you encounter the following calculation. Let's say, let's throw in a 9. Who cares? And you ask what's the answer? I mean, I think most students would freeze at this calculation for whatever reason. Some would do integration by parts incorrectly, whatever, right? Now, if you can use whatever tools you can, and let's say in a probability / statistics course, why not? Then the best way to do this, in my opinion, is the following. Is that you should throw in a 1 over 9. Of course, you have to compensate, right? Because the integral has no 1 over 9 to begin with. But then once you throw in the 1 over 9, you recognize that this is expectation of a square of a random variable that has exponential 1 over 9 distribution. Well, why would that be helpful? Because you do know, right, the expectation and variance of a random variable of an exponential. So that's going to be the variance plus expectation of the square, expectation square. Now it's 1 over 9, then its variance is 9 squared, and its expectation is 9, so it's also 9 squared. The answer is in some way 2 times 9 cubed, whatever that is. All right. Well, the point being is I'm not interested in a final answer, in numerical answer, as you understand, right? It's the structure of the calculation that you should know. And the point is, right, you try to, and this is a very popular theme, you try to match up a certain kind of integral calculation with a density calculation, density slash expectation calculation of something you know. Why? Because you can reuse the result that has been calculated for you without, right, doing the integration by parts again yourself. Any question on this? The second theme I want to tell you is a minor thing, but it could be annoying, is you want to pay attention to without lack of better words, lack of better words, these two guys. What do I mean by this? Basically, notice, right, we define exponential lambda as this, but you will find textbook defining exponential lambda as 1 over lambda e to minus 1 over lambda x. All right. And you understand, there's no point in debating who's right, who's wrong. No point at all. The question is more like, what's the motivation? Okay. And you just have to remember the context to know which one we're referring to by the same name, even exponential lambda. Because what's the consequence? The consequence is, right, for example, if you use this one as your definition, then the expectation is 1 over lambda. But if you use this one as your definition, then the expectation is lambda. Do you understand? Now, which one is which? The answer is this. This one tends to be used more in a probability / stochastic process class. This one tends to be used in a statistics class. I'll tell you the reason why. In a statistics class, you would like to use the sample average to estimate, the population mean. If your population mean is 1 over lambda, then you will estimate the lambda as 1 over x bar, which will be super awkward when you have to operate with this x bar as a random variable. So you rather estimate lambda itself as x bar, which means that you want to go with this random variable. Okay, so I just want to mention that to you. If that sounds confusing, which is which, well, this is no one will go with in this class, so you just have to remember that. But I feel like I should tell you that, there's those things around. Okay, now what's the reason why us, or like this probability / stochastic process people, like this as the definition? Well, the reasons we don't have much business to do with estimation. Well, we might, but then we will put on our statistician hat and do some work there. The reason we like this definition, right, meaning that we like the version when the expectation of x is 1 over lambda, is because it connects well with the Poisson random variable. Okay, like this. So remember what is a Poisson lambda. And by the way, right, the lambda here are not they're the same lambda. It's not coincidental, even though unit-wise they're different. Because here, right, what is the lambda here? The lambda represent the average, right, or as far as you know right now, right, the expected number of events in a unit of time, right, which is what? Let's say 3 earthquakes per month, right, whatever. And really, right, the expectation of x is 3, right? Expectation of Poisson lambda is lambda. So On the other hand, and now let me switch to a different notation. Let's say tau is exponential lambda. What does lambda here represent? Lambda here represent a rate. Oh, well, so this is a rate, right? So lambda here, another name for lambda is, let's say the rate, right? Because it's 3 per unit of time, right? I guess somehow here it's also referred to as a rate, but so lambda here represents the inter-arrival time. So tau here, right, is a random variable representing the time in between events of the Poisson random variable. Technically speaking, right, we have to stretch our context to a Poisson process, which is beyond this class. But Poisson random variable is okay because, you know, you can think of Poisson as events, right? For example, suppose that this Poisson, right, returns a value of 2. That means there are two earthquakes, right, this month. Then it makes sense to talk about the time to the first earthquake at the time to the second earthquake, right, in this month. And then the result is that in between, right, these events, even the time from beginning to the first event is an exponential lambda random variable. Okay, so in other words, the time in between Poisson arrival is an exponential random variable. I just want to show you the consistency of the calculation. Well, what's expectation of tau? So if this is lambda, right? Yeah, this lambda is still 3, right? Because it's the rate of arrival. Then expectation of tau is 1/3, right? According to the 1/λ. Okay, 1/λ definition. Now, does this make sense? Sure, right? Because if you have 3 earthquakes per month, then the average time for one earthquake arrival is 1/3, right? Take the average of 1/3 month for one earthquake to arrive. Does it make sense? And so this is why, right? In probability, we like to use the exponential lambda such that the expectation is 1/λ, because it exactly is the same unit as the one that we use to model the Poisson with. Any question? Okay. So what is the exponential used to model, right? The exponential, so let's say there's some sort of hazard rate model attached to this. But for now, let me just, which is like a topic in actuarial science. But for now, the most basic example, right, is that it's going to be time to some event. Which, by the way, we just talked about right here. If you want, it's really smack in the context of a Poisson model, right? If you have arrival of events according to Poisson, then the time to the event is between events, including, right, the time to the first event. So this is the beginning of time. This is your first event. This is your second event. This is your third event. Notice, right, the length is kind of random. That's because they're exponential, right? Random variable. So time to some event. And you see, for all intent purposes, you can focus on this time from now to the first event. And that's the exponential lambda. So it could also be waiting time, if you will, you want to throw it that way. The reason is you can do that, but you know, uniform is also a waiting time in some sense, right? So both uniform and exponential can be used to model time. So, well, okay, so you ask, so which is which? Who knows, right? This is exactly about modeling. well, you choose the model that's right for the context, and you have to decide what context you're talking about. But I can tell you that, right, a crucial distinction between the exponential and the uniform is that the exponential has no upper bound, right? The exponential has no upper bound in terms of the support. It goes on forever. But don't let this, kind of mislead you to think of this in any crazy way. So the exponential, even though it has no upper bound, a lot of the weight are concentrated on the, sorry, this doesn't go to infinity, right? It starts at 1. And it just tails off, right? Because when x equal to 0, this is 1, right? So most of the weights are concentrated over, let's say, first few units of time. The tail end, the exponential decays very fast, so it's not that much. But, right, so a uniform, so I guess the crucial difference is really, okay, upper bound is fine. But what you want to think about is you can want to compare the shape of the uniform with the shape of the exponential, right? If you have some event arrive or happening uniformly between some time interval, literally you have no idea when it happens, or it happens whenever, right? An exponential, you can see, tends to happen at the beginning, and then it kind of tails off, right? It tends to happen more at the beginning, and then it tails off. Nevertheless, right, this also can be confusing in another way, because the exponential has a famous property, right, that everyone must know about if they work on this. It's called a memoryless property of the exponential. Okay, like this. And it's exactly of the same type of calculation as the uniform, right? Where was it? Well, I'm not so sure in this sense that the uniform is memoryless. Weirdly, I feel like it might be, but it is of this calculation. So if you have waited some time, what's the probability that you will wait some extra amount of time, right? So that kind of calculation happens with the exponential as well. So for some time s less than t, is a fixed time, right? So they're not random. You want to calculate the probability that x is bigger than, you know what? Yeah, it's fine. X is bigger than t condition and x bigger than s. Okay. Now the reason why I was a little bit hesitating is because this can also be written like this, which is a little bit more clear in some context. So, right, clearly h here plays a role of t minus s. So, pick your favorite calculation, right? The interpretation is the same, but some calculations done like this. So anyway, right, what is it? Well, it's going to be probability of x bigger than t over probability of x bigger than s, right? By conditioning formula. And, well, this is just the reverse, right? The complement of the CDF, right? So CDF is this, right? So complement of the CDF is this. So it's going to be e to minus lambda t over e to minus lambda s, which is e to minus lambda t minus s. And you know what? That's exactly the probability that x is bigger than t minus s. And so that's why, right, sometimes this formulation, it's a bit more intuitive, because this would just say this is probably x bigger than h, because t minus s is h, right? So, in that sense, I think the uniform is not memoryless, right? But let's explain why this is memoryless. It's memoryless in this way, right? That basically again, you can think of this is a waiting time, or survival time is another way that the exponential is used. Okay, sorry, survival time. Ouch. Why do we call survival time? Because you think of the event that's marked by the exponential is death or failure of something, right? So the failure of a item very popularly is modeled by an exponential. Okay, and so what happens here? Think of your iPad or your laptop, whatever. It has survived so many units of time, a year, a month, whatever, and you wonder, right, if it's going to survive until next year, right? So this is one, this was two, let's say. So you have used your laptop for a year. What's the probability that's gonna survive until beyond next year, right? If it's truly an exponential, or you use exponential model, you're implying that basically the laptop having been surviving so far doesn't matter. It's just gonna be as if this is fresh, and you're just gonna go through the remaining time as before. I mean, as if it has not survived, right? I think maybe a more easier example to think about is like a human, right? People's age. So if you do think that, okay, again, the exponential this is represent a person's age, so it marks a death, whatever. It's say something along the line that if a person has survived until 60, then the chance that they will survive until 70 is exactly the same chance as like a baby, right? Surviving into 10-year-old. And I think for humans, somehow that sounds wrong, right? But so what that means is that the rate, right, the hazard rate, the rate that people survive change with time. It's no longer constant, right? It changes with time. But if you have a constant lambda, then that's the consequence, right? Or I just want to say that if you use exponential to model the survival time of something or the waiting time, then you must be aware that you have the memoryless property attached. And you must understand what memoryless means. It means that it doesn't remember that has survived so long. Again, right, to demonstrate the point, probability is bigger than a million plus one, condition is bigger than a million, is the same as a probability is bigger than one. Okay, because I mean, you can do one condition x bigger than zero, but right, of course, it's by default bigger than zero, so you don't have to condition on it. Okay, so that's the thing, right? If you have survived a million years, the chance you're going to break down the next time unit is the same as you just start fresh. Again, you may think either way. You might think that something that survived so long should have a higher chance, or something has survived so long should have a much lower chance, whatever you pick. But if you think that way, then you're not really thinking about exponential. Any question? All right. Well, so I just want to draw back to the calculation here, right, with the uniform, and try to point out that it's really not memoryless, right? The reason is because if you look at this, if it were memoryless, the answer here, right, should be equal to probability that u bigger than equal to 10, right? Because it's 25 minus 15. And it's not, right? Because u is uniform between 0 and 30, so probability u bigger than 10 is 2/3. So this is 1/3, right? So it's not, right? The uniform is not memoryless. Okay. In fact, I think if you throw in some small property, then the exponential lambda is the only random variable with a memoryless property. Any question? Let's see what I want to tell you. So you know what? Let's maybe move on to the normal, and then we're gonna kind of do more examples and talk more in depth about these things later on. So back to 5.4, the normal random variable. And well, right, the normal random variables is probably something that you can bet that anyone under the sun, right, might have heard about it at some point. Unlike the exponential, which some people might not have heard, they don't take a probability class. So what's so famous about the normal, right? So the first thing, of course, oh, by the way, I guess it's worth mentioning here that I forgot that if you have an exponential random variable, then if you add something to it and you subtract something to it, it will no longer be exponential. Why? Because exponential, you see, is attached to the support from 0 to infinity. It just goes with the definition. So even though if you add and you subtract the constant, you won't change the density. It will not be called an exponential. And notice, right? I mean, it won't have that time. It won't have that survival time interpretation, because survival time should start counting from 0, and should not have be negative or whatever. Yes, I think some people still want to call it exponential. So I think they call it a generalized exponential distribution or whatever. But I just want to caution you, right? And you see that here, right? Just the definition sometimes is rigid. It doesn't allow you to move things around and still preserve the name. Okay. Anyway, so now with the normal random variable, the normal has two parameters, mu and sigma squared. Okay. And the density will be 1 over square of 2 pi sigma squared. The square root goes all the way out. E to the minus x minus mu, the whole thing squared over 2 sigma squared for x everywhere. So this is probably the first density you see that has density, right? The support is the whole real line. Well, so what's the order of business? The order of business is first of all to check that this is a genuine density by checking that it's non-negative, which is true because the exponential is always positive. So mu, right, clearly can be any number. Sigma squared, by definition of sigma squared, is positive, right? Well, so, but if you try to verify this, right, equal to 1, you might be into some funny business, right? Which is what? Which is trying to find, I mean, if the way you were taught, right, is you try to find the antiderivative of this, which you should know doesn't exist, or rather not recorded, right? It's not named. I mean, some people I think call it the CDF of the normal because obviously, right, it involves a CDF of the normal. But at least in the popular circle calculus, this is not a recorded function, right? It's nothing. So in other words, you don't have a easy calculus way to verify, right, that this is equal to 1, just so you know, right? So on the same level, right, the CDF of the normal, even though a very popular function is used a lot, is not some recorded function. I mean, in some application, I know it's even written as n of x, but this is a CDF of the standard normal. So, which is the integral from minus infinity to x of 1 over square root of 2 pi e to minus x squared over 2 dx, like that, right? That's just its definition, no more, no less. Sorry, I should call it u. So basically what I'm trying to say, right, is that the antiderivative of the normal CDF is something that's not recorded. So yes, there's a way that you can verify this is equal to 1, and yes, you should have seen it in calculus 3, I think, where you try to, right, multiply this with another integral, and you try to look at this as a double integral, and you do a polar coordinate, polar change of coordinate, right? Things like that. I'm not going to repeat it here because we're not here to do calc 3 or polar coordinates, but there's a way to do this, right? But just so you know that the CDF of a normal is not something recorded in calculus. It's not a, I think they call it, it's not a analytic function, I think. Well, I mean, e to minus x squared is not even an analytic function to begin with. I think it's just not an explicit function, okay? Now, I think I mentioned something that I did not write down. If you have the special case when mu equal to 0 and sigma squared goes to 1, you have what is called a standard normal, right? Or some people like to give it the name Z, right? The Z score, whatnot. It's a standard normal, right? When it comes to standard normal, people like to use a Z letter for it. I don't care so much for it. I mean, as long as you clearly specify that you're talking about the standard normal, you just give it whatever symbol you want, right? Right. So this can be checked, but with the tool of calc 3. So what's next? What's next is expectation, right? And people might have guessed that expectation of x is mu and variance of x is sigma squared, right? Well, how do you do this? Simple, right? It's a simple u sub. So I'm just going to point it out once and we're not going to do it again. So if you take x, right, and multiply with this, you see that everything falls into your lap, right? Because you let u be x minus mu squared over 2 sigma squared, right? Then the u is, I don't know, x minus mu over sigma squared dx, right? Yeah. And so this integral, right? I mean, this is basically just integral minus infinity to infinity, right? And then let's see here. So it will be the integral of so you need to do x minus mu over sigma squared, right? So 1 second, let me see how to line this up. So 1 over square root of 2 pi sigma squared here, right? And then so you want to write x as x plus mu, x minus mu plus mu. Right, times, this is basically e to minus u, right? So sorry for mixing the notation, but well, maybe let's just write it like this. Okay. And so well, I need to divide by sigma squared, right? And multiply by sigma squared as well. And so, do I need to? So give me a moment. Okay. So this will be, right? So this part is du, right? So it's going to be sigma squared over square root of 2 pi sigma squared, right? E to minus u du. That's this part, right? And then you plus, right? You still have the mu left. So you plus the integral, right? Mu e to minus x minus mu squared over 2 sigma squared dx 1 over square root 2 pi sigma squared. The only problem is I have a mu over sigma squared here, which I don't like. Give me a moment. I think I'm doing a wrong u sub. Sorry, I think I'm perfectly doing a wrong u sub. Apologize. This is way too complex. Sorry. To take expectation here, right? All I have to do is just to do a plus mu minus mu. So let me see here. If I let u be x minus mu, that's all I need. Then du is dx, okay? And so I will subtract and add mu. Like that, right? And then I add mu to it. Okay. And so this is a u sub, right? So this is just the integral of minus infinity u e to minus u squared over 2 sigma squared du. Here, right, you use the fact that this integral, right, this integral is 1 because it's a density. So the integral here is just mu. And finally, right, what is this integral? You recognize that this is an even function. And this is an odd function. So together is an odd function. Now, an odd function over a symmetric interval should give you a zero integral provided that the integral converge. But it does, right? Well, again, I mean, I guess there's another u sub here in the air, right? You can do that, but whatever. The answer here is equal to 0. So the final answer is mu, right? So that's sort of like the calculation you would do to find the expectation, right, of the normal. The variance is the same, but I guess I won't embarrass myself, right, anymore. I mean, for the variance, you have to do a integration by parts first to bring it down. So anyway, so these are just the facts about the normal, right? Expectation is mu, variance is sigma squared. Now, one thing that is super important about the normal that you should know is that if x is a normal random variable, let's say mu sigma squared, then ax plus b still remains a normal, but with mean a mu plus b and variance a square sigma squared. All right. So again, let's say a linear transformation of a normal remains a normal random variable. right, with the mean being this, because that's just how, right, expectation works. Expectation of ax plus b is a expectation of x plus b. And that's also how variance works, because variance of ax plus b is a square variance of x, right? So that's sigma square right there. Now, why is this fact super important? So it's in a sense, right, I should have stated this result first, because instead of working with a normal in general, you can always pull back to a standard normal, because the standard normal has a much easier PDF, and then do your work there and then transform back to the general normal. In other words, right, if x is a normal like this, then x minus mu over sigma is a standard normal. So that's of course, right, called a Z transformation, if you will. But I mean, it's just, you know, just a fancy name for, right, I mean, this rule. So basically, when you have normal random variables, you can scale and do a location change and it still remains normal. So when you work with normal, it's kind of wise to think whether you can and you should transform the normal into a standard normal, if you have to, especially if you have to work with a PDF, because the PDF, right, of a standard normal is much easier to work with, right? It doesn't have all these bells and whistles. Again, they can be transformed away with the U sub, but sometimes the U sub can be a bit, you know, confusing or whatever with a lot of symbols. So, all right, any question about this? All right, I think the last thing I want to tell you is about, right, the central limit theorem, which is really not what we're going to cover right now, but I just want to tell you the result. Because what the textbook really talks about is the normal approximation to the binomial, which is really a particular application, okay, of the central limit theorem. So it's like this. If you have x1 up to xn, IID, which means independent, identically distributed. I think we talked about this before, right? So they have the same distribution, whether PDF or discrete, whatever, right? Continuous, discrete, I don't care, as long as they are independent and they're identically distributed with mean mu and variance sigma squared. All right. Then if you sum these normal random variables, you subtract away the mean. And you divide it by square root of n times the standard deviation. Sorry, times the variance. Then they approximately have the standard normal distribution. Okay. So again, this looks a bit fancy, but it's really not. The main player here is the sum, all right, of these independent identically distributed random variables. The subtracting the mean, you can see, right, individually make each of these has mean 0. So that's why the mean is 0. The division by square root of sigma square individually, right, makes each of these random variable has variance 1. But if you sum the random variables, right, the variance gets summed. That's why you have to divide by n for the variance, or you divide by square root of n for the standard deviation. So that's why, right? This is that. Okay. So let's talk about, so this is true in general. This is true in general. But in the particular case, when they talk about it, basically they call it, you know, the Morph Laplace theorem, which says that let Sn be a binomial NP, then the probability that a less than or equal to Sn minus n times p divided by square root of np 1 minus p less than or equal to b is going to converge to, so the textbook used this notation, phi of b minus phi of a. Well, what is phi of b, phi of a? Phi of b is phi of x is really the CDF of the normal, standard normal. It's probability that the standard normal is less than or equal to x. Well, if you prefer the letter z, z less than or equal to x. And like in some circle, people use the n of x as the same notation for this. All right. So let's try to see that this is just a particular case of that. Why so? Because if you have binomial n times p, right, then this guy is really the sum of what? Sn is really the sum of n Bernoulli, right? P, independent. Correct? So each of the xi here is a Bernoulli in this case. And so each of the xi is supposed to subtract what? P, right? But if you sum n times mu, if you sum mu n times, that's n times p, right? So this can also be, of course, expressed as sum of xi minus n times mu, but n mu will be outside the sum. That's that. Similarly, right? N sigma square, right there for you, right? The variance of Bernoulli is p times 1 minus p. So like that. And finally, right, by word approximately standard normal is expressed more in details as the probability that this normalized sum is in between two numbers will be close to, right? This is converging to, right? As n goes to infinity. Converging to, you know, how the CDF of the standard norm behaves, or how the probability of a standard norm behaves. So that's central limit theorem. Any question about this? And so, right, just one word. This is probably why, right, the normal is so popular and overused and abused and things like that. The reason is because, right, when you do statistical work or whatnot, right, data science work, summing random variables is something that just occur naturally. And when you sum a lot of random variables and you don't know what the heck is going on in terms of density, you would like to say it's the normal distribution, because then you have an idea of how the sum looks like. That's it. And because this result is very strong in the sense that it doesn't require the terms to have any specific distribution. Anything would work as long as it's independent, identically distributed. That's why it keeps getting invoked again and again and again in many contexts. But that's the same reason why it's overused and abused, because a lot of times it's used without check. For example, it's not checked sometimes that the random variables are independent. Sometimes it's used when the random variables may not be identically distributed. Sometimes it's used when the this is an approximation, right? No one cares to say how large the error would be, because even though it says here as n go to infinity, and right, the sweet number of 30 somehow is invoked. As long as you have 30 numbers here, then you're fine. It's not really true, because this right here also depends on what your distribution looks like, right? If your distribution is a little bit weird, maybe you need more numbers to make the conversions closer to normal, etc., right? So these things are not considerations for this class. I mean, this class, we're just gonna use this and not worry about what kind of error we commit, but you should be aware of, right, why this is popular, and what are the pitfalls when you use the central limit theorem. All right, any question? Okay then. I think it's a good place to stop here, and we're gonna continue next time on Wednesday.
Thank you.
Mhm.